Okay, forces, Newton's laws. How many laws are there?
3. Oh, yeah.
3?
I think, yeah.
Are there 3? Do we agree with 3?
I agree with 4.
3 or 4?
So 3 or 4, depending on where you live?
Yeah.
If you live east of the Mississippi, it's 3. West of the Mississippi, it's 4. Okay. Okay, Sir Isaac Newton, of course, is the guy who comes up with the law of universal gravity, right? And Newton comes up with the 3 laws of gravity. Now, what is the famous story? Yes.
When he's sitting under the apple tree and it falls on his head.
And an apple bounces off of Yoda's head and he says, use the force, right? Right. That's exactly right. That's actually what Newton looks like. He has the flowing locks of the day. And the day happens to be the 1600s into the 1700s. So a good while ago. Yeah, he did live a pretty long time for the times, right? How old was he?
80-something. 70-something. 70-something.
He is old.
Old. There you go. He's old. Okay, long life. He's an English scientist. Not that he, measured the English language or anything, studied the English language. He was from England, right? And his most famous work is the natural philosophy, the principle of mathematics. Of course, that's all in Latin. But among other things, it outlines his 3 laws of motion. Which is kind of bold, because when you say it is a law, that means it's no longer up for testing, right? It is up. He's saying that no matter what, these laws hold, which is quite bold.
How did he die? Old age or was
I don't know. Natural causes, we'll say.
Diseases.
Thinking too hard.
somebody that Julian came back and was killed?
So when we talk about our 3 laws, they're all, their own separate entity, but they're all related. And there's a whole lot of math involved in this, of course, to prove these, because math is the greatest tool of proof. Because at the end of the day, you can't really argue that 1 + 1 = 2. It always equals 2. So math is a great way of proving things, which is why we use so much math in science. Okay? Our first law. You need me to go back?
Yeah, right. For about a couple seconds.
1.
About 10 seconds.
So our first law is what? Inertia. You guys are psychic or smart or something.
Yeah.
Okay. So we have here a hill. What is inertia? Anyone know what inertia is?
Does it have to do with friction?
DJ? What do you think?
Isn't it like is that like a constant? When it hits something or something? I don't know.
Does it have to do with friction?
Like a force
Awesome.
of gravity.
Okay. Anyone else?
Something that makes it slide.
Okay, you're on the right track. I think you guys are. What do you
I
think,
have a
Kevin?
question. Does it have to do with friction?
It can. Friction is a factor. Hannah, what do you think?
When it's rolling down a hill, it'll go faster the steeper the slope.
Mass times.
No. DJ?
Inertia is one of the force, I guess. It's it keeps on going at a constant way until it hits something and then it changes.
That's close enough. I'll take it. Fantastic. It's just the resistance to change. Okay? Resistance to change. So once something is already moving, what does it want to do?
Resist.
Continue to move. Right? If an object is stopped, what does it want to do?
Just stay out.
It just wants to hang out and stay there. Okay? So it's a resistance to change its motion, either speed or direction. Okay? Once an object is going in a certain direction, it wants to stay in that direction. That's right. So, what property do you think affects inertia the most? What property of matter, by two objects, what property is going to change the inertia between one object versus another object? The mass. Okay? So here's my little demo. So we have a little ball, okay, at the top of the hill. We have our little helper down at the bottom. Now our little helper is going to resist the change in motion, right? Catch the ball. And our helper on top has to push the ball, so they are going to change the motion of the ball as well. So, all right, so ball number one. Ball goes down quickly and catches the ball, stops the ball. Small mass. And what happens if we have a large mass?
It'll get ran over. I mean, basically, yeah.
Why?
Because it's a bigger mass.
Okay, it's a much bigger mass. So what about pushing?
So it's gonna require greater.
It's going to require greater force. Thank you, using the word of the day, to start it, and it's also going to take a lot more force to stop it. Okay, so our helper on top is going to coming down, trying to catch it. Nope. Too much, right? The force is too great to resist that inertia. That big mass had too much
Big snowball.
inertia. Okay? So with that being said, we can say our relationship. So small mass equals okay, small mass,
Small inertia.
small inertia, big mass, big inertia.
Wait, so it doesn't have to necessarily stop. It can just like hinder it from like, say if like it was to roll and it looks like something in the way, it like hinder it, slow it down. So it doesn't necessarily have to stop it.
Sure. So that guy slowed it down a little bit, right? Just not nearly enough to stop it.
Yeah.
The process, he ended up being a road bump. He's fine, by the way. Just had a couple bruises.
Next lesson we want to.
Actually, he's in the tug of war coming up.
Netflix.
Same guy.
Is it with a truck?
Netflix.
His friend.
She's involved in the
I
truck
seen
and
it.
the
I
song.
seen it. Truck.
Well, that's gonna go well. Big cruise.
Okay, so let's talk about relationships. Okay? Mathematic relationships, which get applied to science. Like these are relationships, right? We have small mass equals small inertia. That's a relationship between mass and inertia. Anyone know what that type of relationship is called? When one variable increases, the other one increases? What type of relationship that's called?
I haven't been to school.
Starts with a D.
Direct.
Okay, that's, I have just charades up here. So for the D, first word, direct. Second word, if you have a number colon another number, what is that expression?
Ratio.
Okay, a ratio. Okay. If you have two fractions equal to each other, what can you say they are?
Equivalent.
In ratio.
Starts with a P.
Proportional.
They are proportional. So this relationship is a
Proportional.
what?
Proportion.
Directly proportional. Okay, so in our case, when mass increases, our inertia increases, right? They're directly proportional.
Could you speed with mass times acceleration?
Yes, we're going to talk about mass times acceleration. Not in the first law. So what happens when mass goes down? Yeah. Okay, it's like a seesaw or a teeter-totter, whichever one you call it. No, not a tater-tot. Is that a regional thing? Who says seesaw? Who says teeter-totter? Who says tater-totter? Okay, so we have this relationship where both increase or both decrease. So we need the opposite of this one. Anyone know it's opposite of directly proportional?
Indirect.
You would think it is indirectly. Does anyone know? I guess that's not going to work with this going. What? So if you have x and 1 over x, what is 1 over x compared to x? Okay, also known as the, what about x to the negative 1? Same thing, but starts with an I.
Inverse?
It is the inverse. So what would this be called? The opposite of directly proportional. Inversely proportional. So when mass goes up, what happens to inertia? If it was inversely proportional. But is mass and inertia inversely proportional? No. It's directly proportional.
Always?
Yes. So, Thanksgiving.
Turkey.
The more food you ate, the less room you had in your stomach. Okay? That is inversely proportional.
It's kind of like a hypothesis, kind of a if-then statement. So if you want to eat,
Yes. But they have to go in opposite directions. Variables have to go in opposite. One has to get bigger, the other one has to get smaller. And you can do that with anything. The colder the temperature, the more clothes you wear. Okay? Temperature goes down, clothes go up. Unless you're in the polar bear club. And that's all something different. Moving on?
yeah.
Okay. Let's briefly talk about the difference between mass volume, and weight. Those are three different properties. So what is mass? DJ, what do you think mass is? Okay, that's the unit. What is mass? Amount of matter. The amount of matter. Okay? And as you guys grow through high school, bless you, you guys really need to start working on efficiency of note-taking and not writing down everything that is shown. Right? Try to do shorthand, symbols. Volume. What is volume? Please?
The
amount of space. That's right. A throwback to Archimedes. What is the relationship between mass and volume? Density. Remember Archimedes? Density, gold crown, running naked through the streets?
Yeah.
What's the difference from walking on Earth and walking on the moon?
It's like a different amount of gravity.
Gravity. I hear gravity. So gravity. Gravity's different, right? So the moon is smaller. So mass is directly proportional to the amount of gravity. So since the moon has a smaller mass, there's a smaller amount of gravity. So what does that mean about your weight? Okay, so you weigh less. What about your mass? Unless you lose a limb going up to the moon, your mass is about the same, right? So with that being said, what can we say our definition of weight is?
How much gravity pulls down? I don't know, something like that. I don't remember.
That's exactly right. Yeah. It's the effect of gravity on an object. So if you're in a place like a moon, which has less gravity, then you can bound around like you're in a field full of deer. Whereas if you're on Saturn or Jupiter, one of the much bigger planets where the gravity is much greater, you'll be crawling along the ground because the gravity is so great that you'll act like a slug.
Wait, that'd be a good workout though. Because you actually try to record your knees.
That's true. Problem would be getting there. Okay? So with that in mind, let's talk about mass and weight just on Earth. Okay? Our first equation. Mass times acceleration equals force. Okay, this is what you were talking about, right?
Yeah.
And here's our equation triangle. Force on top, mass and acceleration on the bottom. What's the unit of force? Newton, capital N. And we'll be putting this on page 1 here in a moment.
Forces.
So if we have a 1 kilogram object, and notice mass has to be in kilograms in this case, not in grams. So if it's in grams, you have to convert it to kilograms. And you have an acceleration of 1 meters per second, or 1 meters per second squared, and that's going to equal 1 Newton. Now, is acceleration on Earth due to gravity 1 meters per second squared? Now, what is it? It's 10 meters per second squared. So, a 1 kilogram object on Earth is going to have a weight or a force of how many newtons? So you take 1 kilogram, multiply it by, what's our gravity? 10 meters per second squared. So if you have an apple that has a mass of 1 kilogram, then it is going to have a force of weight. Okay? Now we can use weight and use it as a force. Okay? A force of weight of 10 newtons. So that should be starting to be interchangeable. Is that force and weight are the same thing? Actually, weight is a type of force, because weight is dealing with gravity. Right? On Monday, we'll be doing an activity where we calculate the weight of different objects on different planets. So what your weight on Earth would be compared to what it would be on Pluto. Or celestial bodies at this point, because Pluto is no longer a planet, theoretically. So 1 kilogram weighs 10 newtons. Oops, pardon me. Now this, of course, is on Earth. There's always an asterisk on all this. This is on Earth, because this is based on gravity. And in this case, example, is based on Earth's gravity.
Don't underestimate the force.
Yeah.
Man, I put that in there 2 years ago, and I've never had the sound on. So there you go. So what is a force? Any force. Force we're talking about. Yes. Oh, man.
What? Where'd you get these from?
That's ridiculous. A push or a pull. That's right. Ooh, we're going to talk about net forces. Head of the game. Flatulence always make people laugh. So, we can't actually see forces. Okay, we can only see the effects of them. Does anyone know how we represent forces when we're drawing a force diagram, for example? Which we usually do. Arrows? With arrows. Right? If we have a big arrow, what type of force is that? Big force. Small arrow? Small force.
Why did you do that? Why did you put that on there? He doesn't remember it 2 years ago. Okay.
That's ridiculous. So anytime there's movement,
In the bushes.
it is caused by a force.
Microphone on me.
Obviously, no forces, no motion. Now, we're going to change that definition slightly here in a little bit. Instead of no forces, no motion, we're going to change that a little bit. But for now, there's no force, there's no motion.
No wind.
Good. Force arrows. Getting back to what we were just talking about. So, forces are represented by arrows. Small arrows, small forces. What kind of relationship is it between arrows and forces? Directly proportional, right? Small and small. So, big arrows, big forces.
Apples.
You know, when it rains bowling balls. You guys have seen that? That's a great question. So, Julian asked, we're talking about big or small arrows, we're talking about the length of the arrow or the width of the arrow. And that's totally up to you. When we draw our force diagrams, it will actually be length. Okay? It'll be length, because we'll have a scale to where 1 square on a graph paper equals however many newtons. Okay? So he's talking about, are we talking about small arrows as far as lengthwise or actually widthwise? Like if you have 2 arrows, one is this, both of them are the same length, but one is fatter. Okay, I would still, relationshiply speaking, if that's even a word, I don't think it is, I would say the fatter arrow would have a greater force, right? Because it's bigger in some way. Good? Ah! There's our friend again. Net forces. Okay, so this is where we're going to edit our definition. So previously when we said there's no forces, no movement, well, to be more accurate, if our net force equals 0, then there will be no motion. Okay? Because there's always, at least on Earth, there's always a force. Like right now, you're sitting in your chair, and there's multiple forces going on. There's you pushing on your chair, the chair is pushing back up on you, and you're not moving. Okay? So your net force is 0. That's your normal force, but we'll talk about that. Okay, so in this case, our 2, we'll say twins, are pulling on this rope at the same force, 100 newtons each. They are not moving left or right. It should also be pointed out that when we're dealing with forces, and I'll address this later, that when we are talking about motion, motion has to be in direction of the applied force. So even though that they are moving, right, but they're moving up and down, pulling, they are not moving left or right. Okay? So our net forces. And all of our examples will have more than one force. Well, I will say at least one force. Okay? We will never have an example with no forces on something. Okay? It's always going to be a net force of at least one. For example, an object falling into the sky. Bless you. When we ignore, well, I'm getting ahead of myself. We'll get there when we get there. No net forces, no movement. So that's our addendum to our definition. So no forces, no movement, no net forces, no movement. So our net forces is which law? Our second law. What was our first? Inertia. So, if we have this example, where guy on the left ate his Wheaties, and he's pulling with 120 newtons, what's going to happen? Okay, he's going to win, but what does that mean?
Well, this is 20 newtons. Yeah, you want to go down the left, you gotta go to the
Okay, but what does it mean by winning? The rolls which direction?
To the left.
To the left. Okay? So, we could say, if this was a problem, okay, we could say that the guy on the left would pull with a force of 20 newtons to the left. Okay? Because that is the difference between the two. Also, notice that the length of the arrows. This arrow is 20 newtons greater in length than this arrow. It's just kind of eyeball, but it is just length. To go back to what you were saying, Joy.
If you were to play to the war, there might be a lot of factors to into that.
It's actually the number of people. It's actually how many people are on it's the force of surface area, but we won't get into that. Okay, so let's talk about forces on masses. So I'm going to have multiple different examples here and talk about the relationship between force, mass, and acceleration and how they all relate to each other. Okay, back to relationships. So anytime that you put a force on a mass, right, it's going to accelerate at a certain rate. But this also is affected by inertia, right? Because what happens when you get a bigger mass? Bigger inertia. So it's going to take more what to make it accelerate? More force to make it accelerate, right? So we have inertia wrapped in here as well. So if we have this orange, okay? And we push it with this amount of force, okay, that arrow, it is going to accelerate at a certain rate, okay? So that is our baseline. That's what we are, that is our control in our experiment. If we have a bowling ball Okay? Same amount of force. What mass? What's going to happen to our mass here? It's going to go up. Okay, our mass is going to increase. What's going to happen to our acceleration? Mass is going to increase. Acceleration is going to decrease. And our bowling ball, it's hard to get over all that inertia. Okay? What type of relationship do you have between mass and acceleration? Inversely proportional. Inversely proportional. Okay? Mass and acceleration. Inversely proportional. Right? You guys are making note of that. Right? Remind me on Monday where we ended. Okay, inversely proportional to the bowling ball. Right on there, bowling ball. So you can remind me. So we can start this recording up and not miss a beat.
Just get a sticky note and put it on your computer. Yep.